All right. So now let's take a look at what happens for Gauss Seidel. So let's make another figure. And I want to do the same thing for Gauss Seidel. So let's set x equal to zeros again. So for Gauss Seidel, let's again take just the one iteration. So that one iteration is this, right? So for Gauss Seidel, I actually don't need two vectors. I don't need x0 and x, because every time I update x, the xi minus 1 values is already the most up-to-date value, and the xi plus 1 is basically the old value. So it naturally just uses one single vector. So I'm just going to code it up. So x1 is going to be equal to x2, because now x2 is actually the old value, right? Divided by 2 minus dx squared over 2 times b1. So that's the left grid point. And for loop, still the same. And xi is equal to now xi minus 1, which is what I updated in the last I loop, plus xi plus 1, which is the old value. I haven't updated it yet. What? X0 is equal to x at this point, right? This is why in Gauss Seidel I don't need an x0. I don't need an x0 because my x naturally has non-updated values for I plus 1 and updated value for I minus 1. Times bi, and my last grid point, still my xi minus 1 is already the updated value, minus dx squared times b of n. So that's one iteration of Gauss Seidel. Now let's put it for with our expectation, let's put it 10,000. Let's see, start over here. So here I don't need to set x0 equal to x because x is updated every iteration. So I do this evaluate section and end and plot it. So this is what happens after 10,000 iterations. And this is not in scale, but if you compare this solution, I got all the way to less than minus 0.1 compared to the first 10,000 iteration of the Jacobi iteration. We have actually got much closer to the true solution. Let's do that again. Evaluate. Wait, I think I must have plotted it in the wrong figure. What? Is it what again? Oh wait, I didn't hold on. Sorry. So let's do this again. X is equal to zeros, and figure 2. Let me. Is it CLF? Is the right? Okay, yeah. Let's clear the figure and hold on, and then let's do this. This is Gauss Seidel. Evaluate, I get the first 10,000. Evaluate again, I get the second 10,000. Evaluate again, I get the third 10,000. At this point, it's pretty much converged, right? So compare the Gauss Seidel with Jacobi. We can see pretty much that the first 10,000 iterations is roughly at the same location as the 20,000 for Jacobi. So Gauss Seidel converges roughly twice as fast for this case. And as you can see, the amount of work is exactly the same. The amount of memory, it takes half as much, and it converges twice as fast. So there is so if you are not computing things in parallel, using Gauss Seidel is like a no-brainer.